Hello everyone, my name is Dogu Baran Aydogan. Today I'm going to talk about real-time tractography for structural connectivity guided TMS. But let's first start with tractography. Tractography is the technique we use to obtain the structural connections shown on the display using diffusion MRI data. Each of these lines are called a streamline, and the set of the streamlines is called a tractogram. Here the color coding is made based on the seeding location, that is the starting point of the streamline on thalamus in this case. But what is real-time tractography guided TMS? I think this video explains it the best. What we see here is an operator holding a TMS coil. The neuronavigation system aligns the coil and the subject's MRI using infrared markers placed on them. And we have a visualization system that shows the operator the field surface of the brain. Conventional neuronavigation systems can already do this much. But as additional information, we now also show the streamlines obtained with diffusion MRI-based tractography in real time, based on the coil position. I will next try to explain how tractography is done in general, and then how we do it in real time. We start with diffusion MRI data, which looks like this. It is a four-dimensional data. The fourth dimension contains information about diffusion for each voxel in the image. We first pre-process the data and then apply a diffusion model, which provides us a new image that looks like this. This is called the fiber orientation distribution, or shortly FOD image. The color coding here shows the direction of diffusion. Red for left-right, blue for inferior-superior, green for anterior-posterior directions. And the size of these glyphs show the strength of diffusion. Basically, we have information about the direction and strength of diffusion in each voxel. Then we pick a random point in the brain, which is called the seed, and ask a tractography algorithm to find where it connects to. And the algorithm step by step propagates in the FOD image to find the connection. Basically, we only need this FOD image for tractography, which does not change in the conventional or real-time case. What we do, of course, is to do the few hours long pre-processing and the diffusion modeling part in advance. So we only do the tractography part during real-time operation, which takes milliseconds for one streamline. In short, we use exactly the same tractography methodology and algorithm in real-time tractography, and there is no compromise made to gain speed. But is tractography reflecting the structural connectivity in the brain accurately?
An important effort to mention here is the ISMRM 2015 Tractography Challenge. Here, the organizers started with a ground truth tractogram, which was basically a combination of 25 major fiber bundles in the brain. From this ground truth, they simulated diffusion MRI data, which was given to the contestants. And the challenge was, of course, to reconstruct the connections as accurately as possible. The results show the following. Notice here that the x-axis refers to the non-existing or false positive connections, whereas the y-axis is related to the missing or false negative connections. So on average, on individual fiber bundle level, large portions of the bundles were found to be missing. And when they looked at the number of fiber bundle clusters, many groups submitted results that had far bigger than 25 bundles, which were present in the ground truth. The conclusion is tractography has big limitations and there is need to do better. To address this need, we have actually been working on our own tractography algorithm during the past few years. We are using our own parallel transport tractography algorithm, or shortly PTT. We have an open source software called Tracker that implements PTT. It's a command line tractography tool. It's written in C, C++. It has a Python wrapper. It has multi-threading features. It has no dependencies, so runs on a computer cluster quite easily. There's a website with full documentation, and the link is here. Of course, the main purpose of a tractography algorithm is to get accurate representation of structural connections in the brain. The goal is not to get them as fast as possible. And the strength of our algorithm is actually not about its speed, it's about its accuracy. And it has been winning awards in all tractography competitions since 2017. In 2021, we won the Mikai Tractography Challenge with Tracker, and also second and third ranking teams use Tracker as well. I have been working on Tracker since 2015, and this is actually what makes real-time tractography possible in our case, because this application is largely a software project. In Python, what we do is to import a tracker package, initialize it with one line with the FOD image, input seed coordinates, and run. The seed here is a basic NumPy array. That's basically all in its core. For real-time tractography, what we do is to set the seed points based on the information received from the neuronavigation system. Basically, we continuously receive new seed points based on the coil position, obtain connections, and visualize in an iterative fashion.
And we are able to do this because we also have our own open source neuronavigation software called InVisalius, developed by our team member Victor Souza. With our setup, thousands of streamlines can be visualized in a few seconds. Importantly, the results are not worse than what one can obtain with state-of-the-art offline tractography, because the same FOD is used. An algorithm is also identical. Plus, we include all other state-of-the-art tractography practices, such as the use of anatomical constraints. Furthermore, it turns out that real-time tractography has some interesting advantages over its offline counterpart. Firstly, it allows to tune the tractography parameters, which is highly useful in many applications. Secondly, we have a dynamic output, which opens up new opportunities for tractogram visualization. For example, in this case, what we show a concept called the uncertainty visualization, where more transparency is used to show those streamlines that are more likely to be present in the brain, unpresent in the brain. I would like to spend a minute to explain the simple idea behind uncertainty visualization. As I showed for the result of the ISMRM 2015 challenge, it is possible to study false positives and false negatives in tractograms. And it is well known that there is actually a simple way to obtain results that would lay on a band such as the one shown here. The way to do it is simply to sweep tractography parameters. In this case, the FOD threshold parameter, or min FODM in tracker jargon. When we have a large threshold, we know that we will have less false positives. But when we decrease the threshold, then we will have less false negatives. Real-time tractography gives us an opportunity here, where we can in real time sweep through this parameter and visualize those streamlines obtained with lower FOD thresholds with higher transparency. The results look like this. If we combine all the tractograms without uncertainty visualization, we will obtain this. But if we use uncertainty visualization, we can put on with a much richer information about structural connectivity. It is important to highlight the challenges and promises involved with real-time tractography-based neuronavigation. Well, the main challenge is actually involved with conventional tractography itself. Tractography is well known to be limited and it cannot be blindly trusted. When we look at how well tractography matches tracer injections, which is the gold standard, invasive approach for obtaining structural connections, we observe that tractography misses large extents of bundles. Many times, half or more of the bundle is completely missed by tractography. At the same time, when we look at end-to-end connectivity of large brain regions, then we observe that many times streamlines go and end in a completely wrong part of the brain. These are known problems of tractography which we are continuously addressing to improve. If you are curious about where Tracker performs in the ISMRM 2015 challenge, it's about in this band. So we still have work to do. But because we do not have a bulletproof formula for tractography yet, we need to augment it. So what's augmentation? Augmentation here means that we need to complement the structural connectivity information that we are observing on the display. The most accepted approach is to use prior neuroanatomical information, which means the operator needs to know what they are looking after. That is, a fiber bundle of interest in real-time tractography. Another approach is to use electrophysiological recordings. TMS-EEG in this respect is excellent approach that creates a synergy with real-time tractography, which actually opens up new research opportunities. Real-time connectivity information is new. It provides additional information. So we used to look at these when doing neuronavigation. Now we are looking at these. Of course, once you start looking at a neuronavigation interface with real-time tractography, believe me, you will not want to go back. Of course, this also offers new opportunities for both clinical applications and brain research. But wasn't this trivial to begin with? Tractography has been around for 2 decades, so one can wonder what makes real-time tractography possible now? What changed? Does it require the latest and fastest hardware, GPU, CUDA coding, etc.? The answer to that is no. The computation is done in CPU, no CUDA is used. The hardware requirement is quite easily affordable and it's actually not steep. Our tools work in standard laptop workstations. Then does it have to do with the algorithm, or is tracker highly optimized somehow compared to the previous fiber tracking codes? The answer to that is also no. Actually, the computational complexity of our algorithm is quite high compared to many other algorithms, and then this makes it slower. On the other hand, the tracker has increased accuracy, which is something we are willing to compromise for speed. There are actually CUDA-based fiber trackers that are maybe 100 to 1000 times faster than tracker. The natural follow-up question is then, why was this not done before? The answer is this was actually done before. In 2011, in Slicer 3D, for example, a real-time tractography-based application was developed for neurosurgical planning. And in 2014, a software called Fiber Navigator was modified to have real-time capabilities, where one can modify tractography parameters on the fly. So the real-time tractography idea is not really new, it's quite old. But that was also not the main problem that we set down to solve. Of course, one has to have an accurate and fast fiber tracker. It is just a prerequisite. But our main problem is, what's a good way to convey structural connectivity information to the TMS operator so it is most useful for brain stimulation? So what distinguishes our work is mostly the design and user experience. The displaying of tractograms on the peeled brain surface, which is one of the most conventional approaches for TMS, is a natural choice for us. That was not demonstrated before. The dynamic visualization of streamlines, as we do in our work, distributes the complicated connectivity information a long time for the operator to digest it. So unlike previous works, we are showing a movie, not a photograph. The uncertainty visualization is purely made for real-time experience, which is the first time transparency is used to convey information about connectivity. Overall, we do believe we have a unique and working solution for TMS neuronavigation. With that, I would like to end my presentation by thanking the funding agencies and my collaborators who supported this work over the years, and also thank you for listening.